for the boundary layer problem.
Okay, so I'd like to start by thanking the organizers for giving me the opportunity of giving this talk here. I would also like to, again, thank you for coming and welcome you all here. There will be a couple of logistical announcements after my talk. Okay, so I'm going to be talking about boundary correctors and energy estimates for the boundary layer problem. Most of my talk is going to be around the Kato criterion. I'm going to give a proof of the Kato criterion. So for the experts here, I apologize. This is more didactical also for students and postdocs. Okay. So first of all, let me mention a few collaborators in these works. I'm not going to be talking about a single work, but some survey of several works. So there's Dragos Timie, Jim Kelleher, Milton Lopes Filho, Anna Matsukato, Michael Taylor, Idris Titi, and Aibin Zhang, who will be giving a talk tomorrow. Okay, so let me start with the Vanish and viscosity limit, setting up our problem. So we consider incompressible Navier-Stokes in a smooth bounded domain omega. Here we've got our favorite PDEs, boundary conditions, and initial conditions. And as you know, if viscosity is 0, these are the incompressible Euler equations, and we take non-penetration boundary conditions. And if the viscosity is positive, we take no-slip boundary conditions. Okay. So our problem is to understand the vanishing viscosity limit, and we want to make things as simple as possible here. So we're going to consider 2D flow in a bounded, connected, and simply connected domain. I'm going to take an initial vorticity, which is smooth and compactly supported, and as initial velocity, I'm going to take the Biot-Savart law associated to this omega naught. So notice that, of course, our initial velocity is not 0 on the boundary. It's only tangent to the boundary, so there will be an initial layer, but that is not the relevant information here. Okay, that's not going to be the main difficulty. Okay, so U is a weak solution to the incompressible Navier-Stokes with no-slip boundary conditions and this initial velocity. Okay, and our question is, can we find a subsequence of, or some family of viscosities going to 0, such that the associated Navier-Stokes solutions converge strongly in L infinity L2 to something? Okay, and in particular, is this something a weak solution of the Euler equations? Okay, and with velocity in L infinity, L2 and initial velocity U naught. All right, as we know, we have uniqueness for Navier-Stokes in this context, and no uniqueness for Euler because it's too general, even with smooth data. Okay, so first question is, this is a very difficult problem, as we all know, and the first question is, does the difficulty lie in the different boundary conditions? Okay, maybe. So let's do let's carry out an exercise and assume, just for the sake of argument, that the Euler velocity is 0 at the boundary for all time. Okay, and we do energy estimates, and we look at the difference between the Navier-Stokes and the Euler solution. The difference satisfies this PDE, okay, dTW plus the Navier-Stokes velocity dot grad W plus a difference dot grad of U Euler is minus a gradient of something, I don't care what, plus the Navier-Stokes Laplacian term. Okay, we multiply by W and integrate in space, and of course now W vanishes on the boundary, and so therefore, so the nonlinear term as usual is 0, okay, and then we get W gradient of U Euler, plus the gradient term vanishes, of course, equals nu Laplacian of U Navier-Stokes times W. Okay, since W is 0, we can integrate this term by parts, and we get this, okay, and therefore we wind up with the following estimate. ddt of the L2 norm squared of the difference is bounded by the L infinity norm of the gradient of U Euler times WL2 squared minus nu times WL2 squared minus du gradient of W gradient of U Euler. Okay, and then if gradient of U Euler is smooth, we can estimate this by something which we can ground well plus something that's small. Okay, and so therefore we get very easily that W goes to 0 and L2 uniformly in time when viscosity goes to 0. Okay, so we assumed for the sake of argument, that the Euler solution was 0 on the boundary for all time. This actually does happen. It's very restrictive, of course, but one example is radially symmetric vorticity with vanishing mass. So if you take radially symmetric vorticity in the plane with total integral 0, then you get a solution. You get an Euler velocity which is steady and vanishes on the boundary. Okay, and so, for instance, if you take your bounded domain to be a disk containing this radially symmetric vorticity, you've got such an example. And this example was actually considered by Jerry Bona and Jiahong Wu in a paper in 2002. Okay, you can also do superpositions of these kinds of vorticities. So you can take a bunch of radially symmetric vorticities. As long as their supports don't intersect, don't overlap, you also have velocity which vanishes outside of the support, and therefore if you take a huge disk containing all of these superpositions, you have an Euler velocity which vanishes on the boundary for all time. Okay, now this example in particular was considered in a paper that Milton and I wrote with Yuxi Zheng back in 1999, and we even did the vanishing viscosity limit for situations for Euler solutions which are much more irregular, much less smooth than having the gradient in L infinity. Okay? Stuff that includes, for instance, vortex sheets. Okay, now the general problem. Let's see what we learned with this exercise. So the general problem, again, let's try to make our life as simple as possible. And let's take an initial velocity which is smooth, tangent to the boundary, okay? Divergence free, of course, and let's look at the unique weak solution of the incompressible Navier-Stokes equations with this initial velocity and no slip boundary conditions. And Euler is now the unique smooth solution of the Euler equations with the same velocity. Okay, so to take advantage of our little exercise, we're going to look. I'm sorry, I'm getting ahead of myself. So in a short paper, which I only knew about this paper maybe something like less than 10 years ago, but because it wasn't published in a real journal, it was published in the Berkeley seminars. But it's a very, very important paper, and it's become, as Claude mentioned in his talk, it's become widespread in our community. How to prove the following criteria. This has been mentioned several times. The vanishing viscosity limit holds in L infinity in time and L2 in space if and only if viscosity times the dissipation, the integral in time of the dissipation rate goes to 0, okay, in a region of size comparable to nu, thickness comparable to nu near the boundary. Okay, so one of the questions that comes to mind, because, or at least to my mind, because we know about Prandtl theory. Prandtl theory says, assuming that the vanishing viscosity limit holds, things should be pretty much looking like Euler up to a region of thickness square root of nu. Okay, so the question is, where does this O of nu come from? How relevant is this in the proof of the Kato criterion? And to understand this, let's examine the proof. Okay. All right, so one way is easy. Okay, you start from the energy inequality, and then you just put your U nu L2 squared onto your right-hand side. You take the lim sup as viscosity goes to 0 and use the hypothesis of convergence of U nu to U Euler. And the fact that initially U Euler at t equals 0 is equal to U naught, and therefore you get that the lim sup is, of course, greater or equal to 0, less than or equal to U naught L2 squared, minus the lim inf of this object. This is U naught L2 squared. There's a sign mistake here. But in any case, since you have convergence, this converges to U Euler at time t. And since Euler, for smooth solutions, preserves kinetic energy, this difference here is 0. So this side is easy. Okay? Note that the dissipation here is vanishing on the whole domain, not only on a region near the boundary. Okay? Okay, now the sufficiency is the heart of the matter, and here's where you need a boundary corrector. Okay? So again, we do it in 2D for simplicity. We choose a smooth cutoff near the boundary. This is Kato's proof, essentially. I'm going to choose a cutoff near the boundary, so phi is equal to 1 in the neighborhood of the boundary. rescale this, and then you look at the stream function for the Euler solution. Let's see, and here's the boundary corrector, V delta. Okay, so it's the grad perp of phi delta psi. So this object V delta here, it lives near the boundary. Okay? Okay, so U delta is going to be an approximate solution to the Euler equations. It's equal to the Euler equations in the bulk of the fluid, and it's 0 on the boundary. Okay, so in view of our little exercise where we were assuming that the Euler solution was 0 at the boundary, we're going to consider the difference of the Navier-Stokes minus the approximate Euler and see what's left. Okay? So it's enough, of course, to show that this vanishes in L infinity L2 as viscosity vanishes. What are the estimates that we have for V delta, phi delta, and U delta? Well, V delta, the boundary layer term, is of order 1 in L infinity. It's in L infinity L2, it's small. It's like delta to the 1/2. Its gradient in L infinity goes like over of 1 over delta. And its gradient in L infinity L2 is of the order of delta to the -1/2. Okay? This thing here is what's going to change in further applications. Okay? And the approximate Euler minus this term here, which is also the difference between these guys is that this is not divergence free. Okay, so the L2 norm of this difference here is small with respect to delta. Okay, so here's the PDE for W. And it's written, the blue terms is the nonlinear term, the green term is the boundary layer term, and this red term is a linear term. Okay, so we multiply by W and integrate in omega. You can't really do this in 3D. You have to go back to the energy inequality, but in 2D everything works nicely. So you get these three terms here to estimate. Okay, the nonlinear term, the boundary layer term, and the linear term. Okay, so let's start with the nonlinear term, and then you rewrite this as these four terms here. So I've got U nu gradient of the boundary layer, WW gradient of UE. The difference between, this is the boundary layer term again, this is the V delta actually, U nu times gradient of UE, W times this difference here of the two approximate Euler solutions, gradient of UE. Okay? So first thing we do is actually, first thing we do is to integrate by parts the U dot grad to put it onto U. Estimate this using Cauchy-Schwarz. Noting that since we had this V delta, everything is located near the boundary. So you get constant times UL2 near the boundary, gradient of UL2 near the boundary. This term here, you just butcher it, so it's the gradient of U Euler in L infinity, WL2 squared. This is small, and this is small as well. Okay. So here's the term that we don't know how to handle. Okay. The terms that live near the boundary layer are very easy to handle because they're all small. Okay, so they're all of order delta to the 1/2. Okay, and we have the linear term. Okay, we integrate by parts using the fact that W is 0 on the boundary, and then we rewrite this as we rewrite W as U nu minus U delta. So we can perform this estimate here. Rewriting who U delta is, it's U nu minus V delta. And so one of the U nus cancels this one. You get gradient of U Euler and this other term here. So this term here is, again, a good term. It's going to be small because this term here is bounded when you integrate in time. So you get a nu to the 1/2. And again, you get this term which you cannot control. Okay, so you put together all the estimates and integrate in time. Okay? And here's the boundary layer, the nonlinear term, the boundary layer term, and the linear term, okay, as we had estimated. And then we substitute all the things that are morally constants by C's. So we get C times integral of from 0 to T of WL2 squared, something that's small times delta 1/2 times a constant, something, again, that's going to be small times delta to the 1/2 here, and then this bad term, quote, bad term, and then something that's, again, let's see, small. So here are the bad terms, the two terms in the boxes. Okay? All right. i.e. WL2 squared is bounded by this ground-wallizing term plus something that's small plus these two, quote, bad terms. Okay, so to show that W goes to 0 as nu goes to 0 uniformly in time, what you need is that this integral here goes to 0 and this goes to 0 when delta and nu both vanish. Okay, so since delta is vanishing with nu, let's just take delta to be some power of nu. And therefore, what we need is that the max between these two quantities vanish when nu goes to 0. Okay, and we find out. Okay, so then what Kato did was to say, okay, in view of the necessity condition, let's just take alpha equals 1. And then you get that this term here, vanishing, gives you convergence. And if you have convergence, this term, the dissipation on the whole domain, also goes to 0, and therefore you get an if and only if criterion. Okay? Now, there's a simple corollary of our little exercise here is that if alpha is between 0 and 1 and this integral here vanishes, then you get convergence. And if alpha is greater or equal to 1, then this integral vanishing, you also get convergence. Okay, so in a sense, I mean, there's not that much information. I mean, there's not that much into the fact that the boundary layer has to have thickness order of nu. Could have thickness bigger than or smaller than nu. What you have to do is you have to play with the factor in front of the integral. Okay, the factor of nu in front of the integral. Okay, now there's one thing that's a little different than usual here, which is that I'm estimating the nonlinear bad term from the nonlinear term came from the fact that I was estimating the difference between the Navier-Stokes and the approximate Euler instead of Navier-Stokes and Euler. Okay, so the standard thing is to do Navier-Stokes minus Euler, and then you don't really have a bad term coming from the nonlinearity. You have just a bad term coming from the linear term. Okay? On the other hand, this corollary stands anyways. Okay? So, okay. Let me make some comments and extensions. Of course, the same result is true in 3D. It's a similar proof. Instead of doing an energy estimate, you have to go through the energy inequality. Okay? In 1998, Tumam and Wang substitute the sufficiency condition for a condition on a tangential pressure gradient. In 2001, Xiaoming writes a Kato criterion with a tangential gradient instead of the full gradient. 2007, Jim writes a Kato criterion with the vorticity instead of the full gradient. So he's observing that it's enough for the vorticity, the dissipation rate written in terms of vorticity, to converge to 0. Okay, and these two are if and only if. And now, this year, recently, Peter and Igor and Vlad have a sufficiency condition in the spirit of Kato, which includes and extends the unique condition for the convergence, for the well-posedness of the Prandtl equations. And there's something, unpublished work by Jim Kelleher, also related to this. Okay, further applications of this technique and related work. Okay, so in 2008, with Dragos and Milton, we looked at the small hole limit. So we looked at exterior domain flow in the exterior of a very small hole, and at the same time we send the size of the hole to 0 and the viscosity also to 0. Okay? So to be more precise, let U nu delta be a solution of the Navier-Stokes equations in pi delta, where pi delta is a domain exterior to a small hole, which scales like delta. Okay? 2D or 3D, and initial data U naught delta. So U naught delta actually varies with delta. It cannot be the same because U naught delta has to at least vanish on the boundary of delta omega, and delta omega is disappearing. Okay? So you take an Euler solution UE, which lives on some time interval, 0t, of course 0 infinity if you're in 2D, initial data U naught, and you suppose that U naught delta converges to U naught in L2 when delta goes to 0. Okay. Under these conditions, we prove the following theorem, that you can find a constant such that if delta is sufficiently small with respect to viscosity, then this U nu delta, the solution to Navier-Stokes in the exterior of delta omega, converges to the solution of Euler equations when viscosity vanishes in L infinity into L2. Okay? the proof is very closely related to the proof of the counter criterion. In fact, it's very closely related to the proof that I gave, okay, the one where you're looking at the difference between the Navier-Stokes solution and the approximate Euler. Okay? Now, there's one important difference, which is whereas in the proof of the counter criterion, which is a general situation, the gradient of the boundary layer corrector is L infinity L2 norm looks like delta to the minus 1/2. In this case, it's a term of order 1. Okay, so that's what makes this proof work, okay, under this condition. Okay, this is not a criterion. This is an actual, this is not criterion for convergence, if you want, but it's an actual proof of convergence if the hole is small. Okay? Now, in 2009, with Jim Kelleher and Milton, we looked at the expanding domain and vanishing viscosity problem, which is kind of the inverser problem. So let's look at a domain omega r, which is r times a fixed domain, scales with r, and look at the solution of Navier-Stokes in this omega r. Okay? So it's 0 on the boundary, but now the boundary is disappearing because it's going to infinity. In the previous case, the boundary was disappearing, it was becoming a point. Now the boundary is moving off to infinity. Okay? And with initial data u naught r, and you have the Euler solution with initial data u naught, and you suppose that u naught r converges to u naught in L2 when r goes to infinity. Okay, then for any scaling r, which as viscosity vanishes goes to infinity, any which way you want, the solution to Navier-Stokes in the domain omega r converges to the solution of the Euler equations when viscosity vanishes in L infinity at L2. Okay. Before we had a condition for the shrinking domain, we had a condition that the hole be sufficiently small. Here there's no condition at all. As long as r blows up when u goes to 0 in any which way, you get convergence to the Euler solution. Okay, again, the proof is closely related to the proof of the counter criterion. And in this case, the key difference here is that you get something even better. The gradient of the boundary layer term is little o of 1. It goes to 0, okay, when r goes to infinity. That's how come you have no condition on r of nu. Okay. All right, so let's look at the difficulties in the vanishing viscosity problem, the general vanishing viscosity problem. Okay. My comment from before suggests that the linear term is what's responsible because, as I said before, if you do the standard proof, which is you take the difference between the Navier-Stokes solution and the Euler solution, the nonlinear bad term is not really there. But the linear term, the bad term coming from the linear term is still there. So is the linear term responsible for the difficulty? So if you consider 2D flow in a disk, okay, with radially symmetric vorticity, you eliminate the nonlinear term. All that's left is a linear term. Okay, and Navier-Stokes equations become Stokes equation. But then this Stokes solution converges to the Euler solution. Okay, so this was proved in 1994 by Matsui for smooth data but non-compatible boundary conditions. Okay, in other words, 0 and then for Navier-Stokes, no slip and non-penetration for Euler. And Jerry Bowen and Jahong wrote a paper that I mentioned before for continuous initial vorticity with compatible boundary conditions. Okay, and you get the same result if you take a radially symmetric vorticity with a boundary that's rotating at a speed which is even bv in time. Okay, and initial velocity is only L2 plus circular symmetry. Okay, so this is a couple of papers that we wrote with Anna and then with Anna and Michael Taylor. Anna Matsukato and Michael Taylor in 2008. So it seems that the linear term is not really what's responsible for the difficulty. So the question is the issue the difficulty coming from the non-compatible boundary conditions or from the nonlinear term? Okay, to understand that, let's change PDE for a moment. Okay, so let's look at the Euler alpha equations, which are given by this system here. Okay. So we have ddt of v plus u dot grad v plus this weirdo term here, sum in j, vj gradient of uj is minus the gradient of pressure. U is divergence free, and v is u minus alpha squared Laplacian of u. Okay, so this is the object that is being evolved here. Okay, but it's evolved by this velocity u. The relation between v and u is v is identity minus alpha squared Laplacian of u, or u is identity minus alpha squared Laplacian inverse of v. So u is two derivatives smoother than v. So you're evolving v with something that's smoother than v. Okay, it's a regularization of the Euler equations. U is called the filtered velocity, v is the unfiltered velocity. Now, the Euler alpha equations arise as the inviscid case of second-grade fluid model, the inviscid Kamm-Masse-Holm equations, and also as the geodesic flow on the volume-preserving diffeomorphism group with the induced H1 alpha. I should have put H1 alpha metric. Okay? In a bounded domain, this doesn't come with boundary conditions, so this is not really a physical problem, but it is a problem of mathematical interest if we're probing where the difficulty in the vanishing viscosity limit is coming from. Okay? So from a mathematical point of view, since given the order of the equations, it's natural to assume the no-slip boundary conditions. U is 0 on the boundary. Okay? What kind of estimates do we have for this equation? Well, if the initial velocity u naught is h3 intersect h1 0 and divergence free, first of all, you have existence and uniqueness of the solution to the Euler alpha equations, which is global in time, and this is a result that was originally included in the paper by Taranesco and Giraud in 1994. It's explicitly mentioned in Valentina's work from 1999, and there's a different proof, a geometric proof in Margin, Ratu, and Scholar, 2000. Okay? What kind of a priori estimates do we have? Well, first of all, this H1 alpha norm is conserved, so it's the L2 norm of u squared plus alpha squared times the gradient of u L2 squared. Of course, if alpha goes to 0, you're losing this estimate here. Okay? Also, the curl of v, of the unfiltered velocity, is transported by a divergence-free vector field u, or u alpha, and therefore the curl of, this is the curl of v, curl of u minus alpha squared Laplacian of u, so that the L2 norm of this guy is also conserved. Okay, so I'm going to introduce something called the suitable family of approximations. So if I take an initial velocity, which is h3, divergence-free and tangent to the boundary, I'm going to say that u0 alpha is a suitable approximation to this. If it vanishes on the boundary, it converges to u naught as in L2 when alpha goes to 0. Its gradient is little o of 1 over alpha. That's initially only, that's the initial data assumption. Okay? And the h3 norm is of the order of 1 over alpha cubed. Okay, for any u naught in h3, divergence-free tangent to the boundary, it's also always possible to construct such a family of approximations. So for these approximations, you work a little bit harder, and you get the following a priori estimates valid for all t. So the h3 norm is controlled by 1 over alpha cubed, which is the assumption on the initial data, comes from the assumption on the initial data, together with the estimate on the curl of these v alphas. And the gradient of u alpha, there should be a t here. Time TL2 is bounded by 1 over alpha for all time. Okay, so with this setup, we have the following result on the vanishing alpha limit. This is a theorem, a preprint actually. It's submitted with Milton, Idris, and Ibn Zhang. If for any capital T fixed, if you take an initial velocity for the Euler equations, which is h3, divergence-free, tangent to the boundary, and you look at a family of suitable approximations, you look at the corresponding alpha Euler solutions, u alpha, then you get the convergence not only in L2 of u alpha to u Euler, but also you get this supin time of this dissipation rate, if you want, alpha squared times the gradient of u alpha L2 squared. This is vanishing when alpha goes to 0. Okay, the proof follows along the proof of the Cotter criterion. In this case, if you try to do the similar exercise that I did before, in which you compare u alpha minus u delta minus the approximate Euler, it doesn't work. Okay, so you really have to compare u alpha with u Euler. Okay, write an equation for w, multiply by w, integrate in omega, and then in time, use the boundary corrector v delta as we did before, and you end up with this estimate here, okay? Okay, so you look at this estimate and you say, okay, this is under control. Initially, it's going to be 0. Alpha is going to 0. This is my ground wall term. This is small. This is small. This is small. So I've got this alpha over square root of delta here, and then I have alpha over square root of delta squared. So as long as alpha over square root of delta squared goes to 0, when delta goes to 0, you're fine. And we have this liberty here. So you get convergence. And details about this will be in the talk by Aibin Zhang tomorrow. Okay. So what have we learned? Euler alpha with no slip, you have non-compatible boundary conditions and nonlinear, and yet you still have convergence. Okay? So the difficulty does not come simply from the different boundary conditions. The difficulty does not come from the linear term. It's a difficulty due to the nonlinearity. Well, the Euler alpha equations are also nonlinear. Okay? However, the thing is that Euler and Navier-Stokes, they have a very special nonlinearity. It's not the same. Okay? For both Euler and Navier-Stokes, the shear flow, or if you want vortex sheets, plus the nonlinearity give you Kelvin-Helmholtz instability. You do the linear stability analysis, and you get these exponentially growing modes. Euler alpha is not subject to the Kelvin-Helmholtz instability. You do the linear stability analysis, and you don't get the explosion of the higher modes. In fact, the vortex sheet problem is completely well posed for the Euler alpha. This was proved by Bartosz, Linschitz, and Titi, Claude, Jasmine, and Idris in a couple of papers, 2008 and 2009, where they also did the linear stability analysis for the Euler alpha equations. Okay, so now the different boundary conditions, they lead naturally to a vortex sheet on the boundary. Okay? And this is why the absence of the Kelvin-Helmholtz instability is relevant. Okay, that's an explanation of why we actually do get the convergence for Euler alpha, or at least my point of view. So in at least one instance, we've shown that the absence of Kelvin-Helmholtz instability leads to convergence. The Kato criterion is designed to rule out the Kelvin-Helmholtz kind of instability near the boundary, or if you want, the creation and amplification of small scales at the boundary. Okay? Now, the Kato criterion presumes that the solution to the Euler equations is smooth. Okay? And the question, should it be? Is that a good assumption? Is that a reasonable hypothesis? Okay? Perhaps instead, we should be studying the vanishing viscosity limit for Euler solutions with vortex sheet regularity. Okay? In this case, we may have convergence without the Kato criterion being satisfied. Okay? On the other hand, existence at this level of regularity is not established, has not been established. Okay? For general vortex sheet regularity, it's not proved, and these problems, I believe, are intimately related. The lack of an existence result and the vanishing viscosity limit. And of course, it's very far from the uniqueness setting. Okay, we don't even have existence, let alone uniqueness. Finally, what about the thickness of the Karyotype boundary layer? Well, in a sense, my understanding is that it's not that all that physically meaningful, but on the other hand, there is a sort of a PDE miracle that this thickness of order nu does provide us with an if and only if condition. So I at least don't understand this all the way to the end. And I guess I finished a little early. Thank you.
Are there questions or comments?